So without further ado, I'm going to invite our first speaker to come kick it off for us. Three really awesome talks in the first parallel session. And first up is Sendhil. Thanks.
All right. Thank you very much. In the spirit of informality and trying to just, I'm just looking at the time. In the spirit of informality and trying to throw out some ideas, I wanted to talk today about something that I've been just sort of thinking about, have some evidence on. It's joint work with John Kleinberg and Annie Liang. And I mainly want to start a conversation. I think we've got some interesting results, but hopefully you'll get a sense of what I'm talking about. Here's the issue I'm focusing on. I think that, as everyone in this room understands, machine learning provides a framework for generating very good predictions off of a large scale of data. And in fact, I'd say their power, machine learning algorithms' power, comes from finding signal in some unexpected places. And as a result, a consequence of that is that it's accused of being atheoretical, which is probably somewhat true. If we were theoretical, we'd pick the variables based on theory and subset and choose substructures. But we're exactly using the fact that we don't need to our advantage. So there's, and so this is, so the question I want to ask is, as an empirical social scientist, I'm often in the business of testing theories, which raises the question, for me at least, how can I use ML for this task? Are these two really dissonant with each other? Do they really have, does one thing stand in opposition? To do that, I want to just start with a fun example from work many people have done in behavioral science. And so this example is the following. Suppose you're looking at the flips of a coin, and I want to ask you what comes next, head, head, head. What are the odds of the next thing? Now, you guys will probably say, oh, 50-50, it's a fair coin, 50% chance of tails. But in your heart, you know what the next thing is going to be. Right? Similarly, you kind of feel like, yeah, it's not going to happen here. Now, this intuition you have is pretty true. No, it's not mathematically true, sadly. But it is true about the intuitions we all share. And this is, there's some appealing theories of this. One is called the gambler's fallacy. The idea is that runs can't go on for very long. Another quite well exposited theory is what's called the law of small numbers. People expect small data, small samples, strings of 4, to have statistical distributions that you normally expect from large samples. So the odds of a very long string is low, but people think the odds of a string of length 4 being all heads is also very low. So there's some theories that we've developed to do this. This has some pretty big implications, as you can imagine, say in financial markets or in something even more important, sports. But you can see how this is the kind of theory you might be interested in. Now, suppose I were to go test this theory. How might I do it? Here's an example of how you might test it, which I'll show you. Here's an experiment we ran on Mechanical Turk. It's actually kind of fun. You tell people, you want to just generate coin flips. Our coin is not working, so we just want you to generate heads and tails. I mean, it just turned out to be a lot cheaper to use you than to use a coin. We tell people we're going to generate 8 flips of a coin, just go ahead and generate 8 flips. They actually are told you get rewarded for being as random as possible. We have an algorithm to discern if you're being random enough. So we're important seeing how people do at this task, so it is important to us that you actually not flip a coin or use some of it. So we get a bunch of strings. In the end, we have about 14,000 strings, but you can run this and generate lots of random numbers. So now, what would you do? You take data like this and you'd look for some patterns implied by the theory. You'd say, so here's actually, look at the number of, you can see runs are kind of under-generated. Runs of length 2 are much more common. Runs of length 3 are less common, 4, 5, 6. People just don't expect very long runs. So here is the Bernoulli distribution. Here's the empirical distribution. Similarly, look at the number of heads that Bernoulli would imply on a string of 8. They're exactly half-half is grossly overrepresented. People expect strings of length 8 to have exactly half, much more often than they actually do. So in this sense, I've simply created an experiment that recreates an intuition that psychologists have with a large amount of data, and the theories match up what you would have expected and predicted from the data matches the theories. The question I want to ask, and that didn't require any machine learning, the question I want to ask is, well, are we testing these theories well? This is what you might call a prediction of accurateness, that is, correctness. Did the predictions hold in the data? And in fact, in this case, they did. And most often I would say, this is what we do in social science. We test whether our theories are correct. And you might say, well, what else could we be doing? But again, in your hearts, you kind of know there's something else we want to know, which is we want to know, are our theories complete? That is, I found this one pattern in the data. My theory made this one prediction. It happened to be true. But did it capture everything that could be modeled in this data set? Are there other things that this theory might be missing? Being correct is not the same as being complete. And so what I really would like to know, this is a burning question. I just put that up there so that you guys would believe it's an important question. I mean, I thought of making burning in red, but it felt like it was a little overkill. Plus, I'm colorblind. That could have ended up green. It would have been very confusing. But how can we ever answer this question? This almost feels like one of these philosophical questions. That is, that we can answer it as science moves forward, and we say, oh, the theory wasn't complete, because someone else found another theory that has another prediction that's true, and your theory didn't have that. But beyond that, beyond the discovery of new things, how can we test it? So to do that, I just want to point out that the real problem we lack here is a benchmark. What we don't know is when a model, in this case, these models capture some of the relations in the data, we don't know how many relations there are to be captured. Let me just go back to one issue and then you'll see what I mean. Suppose I did a machine learning task in some data set involving human beings or involving anything, and I find a certain predictive accuracy. Is that a good predictive accuracy or a bad one? It's very hard to tell. If it's digit recognition, we know what we should be getting to, 100%. But in most other domains, we don't know the benchmark. We don't know what is good, because we don't know what is complete. And that's the essential problem here. So just to give two examples, if I was modeling, I assume that's the solar system. If I was modeling planet dynamics, I'd hope to get predictive powers that are closer to digit recognition. But if, on the other hand, somebody came to me and said, you know, I've got this model, it's accurate at 51%, but, you know, it can predict up, down 51%, but it happens to be that up, down is movement of stock prices, 51% is pretty awesome. In fact, I would have a red carpet and first-class tickets if I could get 51%. Which, by the way, I didn't know you're supposed to get all that stuff, so already. Susan was nodding, so I don't know what that means, but, you know, whatever. We're not gonna litigate this now, up here. So the point being that the underlying reality tells us how complete we can ever hope to be. And so should we be satisfied with 60%, blah, blah. And the distinction here is the distinction between modeling error, which is what I'm trying to capture, did we get complete enough, and the intrinsic noise in the problem. So what I want to say today is that I think machine learning, exactly because it is atheoretical, can provide a benchmark. It can tell us how far can our theories get to. The fact that machine learning is not putting in much structure and is simply just trying to churn out predictions without much consideration for theory, it tells us, at least gets to the point of saying this captures some notion of the total predictability in the data. And if it captures some notion of total predictability, we can ask how close are our theories to that notion. And it gives almost theory a place to get to, which I think is super important from a theoretical point of view. Let's go back to our example and see what we do. So in this example, what I need to do is, let's take this task, a continuation task. Given the first 7 flips, remember I have data with 8 flips length, what is the probability that the 8th flip is H? So let's turn this into a prediction problem, which is, it's a prediction rule from the strings of HT7 to a probability between 0 and 1. And you can imagine putting a very trivial error structure on that prediction rule, because it's just binary prediction. A second prediction problem I'll put on here is not continuation, but classification. I give you strings of length 8, and I ask you to classify whether it comes from a human or from a coin. So 2 very simple prediction problems, trivial in a way. They're both noticeably very simple classification and prediction rules. Notice they go from the space of HT to the 8th. That's 2 to the 8th, and I'm sure some of you could work out what that number is, but John tells me it's not too big. And those rules can be turned into a classification problem, okay, or a prediction problem. So as a result, I'm just going to take those prediction problems and I'm going to apply a theory to them. Here are 2 very well-known theories. I'm not going to go through them in detail because I've got 6 minutes and 35 seconds left. I could still keep counting down, I suppose. The first theory is similar to the second. These are the best theories, I think, in this area for understanding human perceptions of randomness. They basically say people act as if there's an urn of a certain size and that urn is getting refreshed. So instead of sampling without replacement, instead of sampling with replacement, people act like we're sampling without replacement. So you can see how that generates the gambler's fallacy in many of the things we saw. And there are parametric versions of these models. These are very good models. They match all the predictions we've already know to have. So now let's apply these models to the data we have. Okay, so I'm going to turn these models into a prediction exercise. I'm going to use these models to predict whether the next flip will be heads or tails. I'm going to use these models to predict whether a sequence will be generated by humans or not. And so I'm going to estimate the parameters of the model in 9 folds and evaluate it on the 10th fold and use cross-validation to just see how it does. And here's the prediction error. If I guess 50-50 for both of these tasks, I get 0.25. That's just how we set up our loss function. And you can see these models have performances. You always think it's a bad thing when you have to get out to 4 digits. But they have performances at 2495, 2491. Now, is that big or small? This is the point I said earlier. Who knows? That could be tiny. These models could be doing nothing, or there could be a lot of intrinsic noise in this system. So how well are these models doing? Now, what I can tell you is all of the features that we talked about before, long run lengths, all of that, they're exactly designed to match those, and they are correct. But how complete are they? So to do that, now I'm going to fit a machine learning algorithm to the data we have. And I'm going to use an algorithm that's super complicated, so I want to make sure you guys follow along. It's called table lookup. The reason we designed this algorithm, the reason we designed this context is because we want to abstract from the specificities of any one algorithm. 2 to the 8, as I said, is a small number, I think, I hope. John claims it is. 256, there it is right there. And therefore, we can literally populate the table. That means we have the exact best prediction that anyone could produce. So we're not going to litigate whether we use the right machine learning algorithm. So now I've got a completeness measure. And so again, I'm just going to use table lookup to come up with the table lookup prediction rule. And now I have a benchmark. I know the best anyone can do in this problem, and I can see how well the theories do. So there's good news and bad news. The good news is the theories end up at about 0.2427. So this already tells you how bad these scales can be. Like if I told you I have an algorithm that does 0.2427 and random guessing would do 0.25, you would have said that's just stupid. But guess what? That's the best you can do in this problem. That is the inherent amount of structure in this problem, which is actually quite a bit of structure, because if this were finance prices, which this kind of mirrors, people making guesses, that's a lot of structure. But it just shows you the units that are wrong. The other thing it tells you, though, is it tells you that this is the relative fraction, the distance between 0.25 and what the models do and what table lookup does. So our theories in this context are only about 13% of the way or 9% of the way towards capturing all the structure that is in the data. So while the theories are intuitive, there's just a lot more structure to be found. So let me just talk about the problems with ML as a benchmark. The first thing that I just want to flag with this idea is that it might be too high of a benchmark, because we worry about overfitting, but normally we worry about overfitting the noise in the data. But there's a different kind of overfitting problem that this creates. It's overfitting the very specific context. Theories are created because they work well across contexts. Nobody really cares about coin flips. They care about the things that coin flips are metaphors for. So in a way, if an algorithm does very well at predicting coin flips, that might be too good, because that knowledge is not going to transfer to the other context that we really want. So that's the first problem. So to deal with that, what I'm going to show you is I'm going to show you an interesting experiment. The experiment is one where these are loan officers who are paid to screen loan files, and they're asked to approve or not approve these loans, and about 2/3 of them are good. The files are given to them randomly, so there's a lot of information. But as a behavioral scientist modeling this, I would say, you know what's funny? I wonder if the first few files being good would lead them to say, I can't have 4 good files in a row. I better get the next one wrong. I better nix the next one. So you can see this problem has in it the structure of random generation of coins, because it's head, 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 tail becomes approve, not approve, approve, not approve. So what I'm going to do now is something that's going to feel a little ambitious, but I'm going to just generate data on Mechanical Turk of 0, 1 variables, biased, have people generate coins that are 2/3 biased. That's going to give me the same structure as the previous problem. Train table lookup. And then in this data, which has nothing to do with coins, take the algorithm I trained on table lookup, trained in the mTurk data, and apply it to this data. In other words, I'm going to transfer the algorithm, because I'm interested in contextual overfitting. If what I found in mturk was just fitting things about Turkers generating coins, it shouldn't transfer very well. But what's kind of striking to me was that it transfers at about the exact same rate as it did in data. If you remember, in data it had about 0.2430. Table lookup trained on Turkers transfers into this case at about 0.2441, which is only slightly worse. Which in this context tells us that what the algorithm found, what table lookup found as structure in the data actually seems to be about structure, about human perceptions of randomness. The final thing I'll tell you very quickly is the limited success of theories due to weak features or weak ways of combining them. So here we did the most trivial exercise, which is an actual algorithm. We formed a set of features, which are the features broadly implied by the theory. But instead of using the theory to structure the combinations of features, we just let a bunch of interaction terms and threw them into lasso. We could have done a decision tree, we could have done whatever. And we asked, so this means we're sort of theoretical in feature creation, but not theoretical in structuring how the features interact. And in fact, it turns out this approach, which is lasso, actually gets us about 70 or 80% of the way towards table lookup, which makes you feel that we've done 3/4 of the work of finding the kind of things about randomness that matter, but not the parametric work in figuring out how they come together. And so that could be a lesson to say we shouldn't expect theories to do that parametric structuring, but expect theories to point us to features. Or it could be a lesson to say, actually, we need to understand what's wrong with the parametrics. And that's a question of application. Let me conclude here and just say, to me, I hope there's a playbook here, which we are trying in examples, other examples, which is just whenever we test theory, you can always add this to a hypothesis test. You can kind of turn it into a prediction task and then do an atheoretical ML as a benchmark so that for free, whenever we're testing a theory, we're also getting some gauge of its completeness. Okay, let me stop there. Thank you.
So we can take, as Susan comes up, we can take one question for Sendhil, and then we'll have the rest of the questions for the panel. Any questions? Yes, in the back, Michael.
I really found that question, that second point about theoretical machine learning. Should the peer review process have that kind of filtering, editing mechanism for papers?
I would say that I think that it is, this paper is obviously not solving that problem, but I think hopefully in the future, just like we have p-values for correctness, if there is a procedure for completeness, we start paying attention to that.
All righty, next up is Susan.
All right, so I'm really honored to be here, even though I sat in coach on my way. Unlike what at Sendhil, I think I leave a more glorious life than I do. So when I realized I was talking after Sendhil, I realized we might have had a more fruitful discussion if I'd presented some other work, but I just put up a shameless advertisement that we can come back to in a discussion for work maybe that I will try to present next year. So my student, Stefan Wager, is giving his job talk today at MIT, stats on some work on machine learning and experiments. So we can talk about that some in the discussion. But what I'm actually going to talk about today is a paper that I think has the absolute worst title of any paper I've ever written, but nonetheless, hopefully will be more exciting than it sounds. So what we're trying to do in this paper is think about better techniques for evaluating the results of experiments in network settings. And this is something that I've been working on in practice in thinking about seller networks, and my co-authors have been working on using Facebook data. So, really the goal of the project is to try to, how do we tell if my outcome is affected by my peers' treatment? And I mean that very broadly, so not just my neighbors, but maybe my strong ties or my weak ties or my friends of friends. How can I test those kinds of hypotheses? There's lots of jargon for this in different literatures, but ultimately it's about network interactions. And it might seem that if we had a randomized experiment, like everybody in this room believes that when we have randomized experiments, things get very easy, right? Except for in networks, they don't. So, what are some of the problems? Everybody who works in network experimentation is familiar with this. Even if I have a randomized experiment, so this is my network and my yellow guys are treated and my blue guys are control, what do I do when I analyze the results? My observations aren't independent if it's an interesting network. Peer effects may be present. My individual outcome is really a function of the entire network's treatments. And so there's an explosion of possible outcomes for each individual as a function of the randomization. And then if I want to do a standard error, like the whole reason we're doing randomized experiments is we want to get a result and get valid statistical inference. What does it mean for the net to do asymptotics as I increase in what's changing? Like I must be changing my whole network. But like if I'm looking at MIT students, I'm interested in MIT students. I'm not interested in some hypothetical university twice the size of MIT with some more complicated network structure. But to date, most of the work about doing inference in this area has required you to specify a model of how the networks grow and how the links form as you grow, when that's just really often not the question you're interested in. You have a network and you want to see if you have valid results on that network. So that's what we're going to be working on today, and we're going to use an approach called randomization inference, or that's also called permutation tests. And so just starting out in the simplest case, if I wanted to see what was the effect of a treatment, I can think of these W's here as my notation for the treatment, and this is potential outcomes. So yi of 0 is what my outcome would have been if I wasn't treated. Yi of 1 is my outcome if I was treated. And so if this is my data, well, if unit A was treated, then I know their outcome when they were treated, but I have a question mark. I don't know what their outcome would have been if they were controlled. That's the fundamental problem of causal inference. Okay, so then what do I do with this data? Well, if I want to test a particular null hypothesis, if it's a sharp null hypothesis, that means that I actually can figure out what my outcome would have been if I'd had a counterfactual treatment status. So, for example, the sharp null hypothesis that there's no effect of the treatment on anyone allows me to fill in this table. So if I, under the model implied by my null hypothesis, I know exactly what your outcome would have been if you hadn't been treated for unit A. Okay? So if this is now what my null hypothesis implies, I can actually do this randomization inference to get an exact p-value that doesn't rely on any large sample approximations. It's the exact p-value for this experiment, for this network. And again, in the context of networks, that's super important because I have the network I have, not going off to infinity. So the way that you do this, and this table is a little busy, but I'm going to be building on this concept, so let me take a minute to go through it. So here are my actual treatment assignments, and again, this is my table before giving my actual and counterfactual outcomes for each unit. Then I can consider, though, there could have been other treatment assignments. Other vectors of treatment assignments could have been realized under the experiment. And so if this was all equally likely, then I would have these 1/6 probabilities if I was going to rerun the experiment over and over. And so under my null, I know exactly what the outcomes would be under each of these treatment assignments. And so I can calculate my test statistic, the average outcome for the treated minus the average outcome for the control, under each of these counterfactual assignments. And so that's going to tell me the distribution of my test statistic under my null hypothesis, and I'm going to get an exact p-value. Okay? So this is actually a small subset of people have been using this quite regularly in the network literature. It's often not something that you teach or think about sort of outside of that because it seems in some sense fairly limiting to be talking about this very special class of sharp nulls. So in this paper, what we're going to do is actually try to extend this idea to a much larger domain of hypotheses. So in this example here, I knew I had a very strong null. The treatment has no effect on anyone, and that's how I was able to figure out your counterfactual outcomes. But if I had a more complicated null, like that you can have an effect of your treatment on you, but then I want to test a null that there's no peer effects, this looks like it would all blow up. Okay? And so we're going to show you how to make it not all blow up, and we're going to test any hypothesis of the form treating units J related to unit I in way Z has no effect. So friends of friends have no effect. Weak ties have no effect, but strong ties do have an effect. The position of your peer in the network has no effect relative to, so a peer who doesn't have a lot of friends has the same effect as a peer who does have a lot of friends. All the interesting hypotheses of that sort you would want to test all fit into the same framework. Now I want to be very clear. We're going to give you a p-value. We're going to reject the null of nothing. I'm not going to give you a confidence interval around a positive effect without much, much stronger assumptions. So the way I think, though, that this should be used is pretty much any network experiment paper should apply this method first to say, I'm going to get a very, very clean measure of whether there was any effect of type Z. Then I might estimate a model and put on a lot more assumptions to actually, if I got a positive effect, to get a parameter estimate and confidence intervals, but those confidence intervals on the parameter estimate are going to require a lot more assumptions. They're going to require some kind of asymptotic theory about the network formation and so on. And so we're extending this in future work, but today that we're not going to be able to deliver beyond that. In the paper, we talk about how to develop powerful test statistics and as well aspects of experimental design. So just to show you that this isn't obvious, this Nature paper that analyzed this very famous Get Out the Vote experiment on Facebook had some claims in it about the hypothesis tests about peer effects. They said the messages not only influence the users who receive them, but also the users' friends and their friends of friends. Okay? So very huge experiment, very widely cited experiment that telling that your friends influence your decision to vote. So what you would do, what they did in the paper, turns out to be wrong. So let me tell you what you might have done if you were thinking about extending randomization inference to this setting, and then I'll tell you what you actually should do. So what you might think you would do in a randomization inference setting is you would choose some test statistic that measures interference or spillovers. For example, you could run a regression of the outcome on the number of treated peers, take that coefficient, and that's your test statistic. Or you could use an edge level contrast between edges that have treated peers and controlled peers. Take the observed value of that test statistic, and then using what randomization inference would suggest that you should do is then think, well, what are all the other vectors of treatment assignments that could have occurred? Let's now draw from that distribution. So I'll randomize over the treatment assignments, and I will use a table like this one to say, well, I'm under my null, the treatment had no effect. Okay, but the problem is what they're trying to test is actually spillover effects, and they know that there's a direct effect of the treatment. So that box was wrong because what they are assuming when they do this approach is that there was no effect of the treatment on you and no effect of your peers on you. And so what you can find is that actually you're going to end up having an error rate, the type 1 error rate 3 times too large, because essentially you're assuming that when you permute the treatments, it doesn't actually affect your own propensity to vote, and that's just wrong. So you're going to get way too tight of the error bands. Okay, so if this is wrong, well, you could just criticize them, but actually what we want to do is show what the right way to do it is, and in fact that you can still do this exact same approach. So what I'm going to do instead is something that seems a little funny at first, but hopefully you'll wrap your head around it with some examples. So I'm first going to select a set of focal units, and these are the people for whom I'm going to examine their outcomes. So I'm just going to pick a set of units, and later we'll talk about how you pick those units. And then I'm going to choose a test statistic that's a function of the treatments and only the focal units' outcomes. So instead of looking at everybody on Facebook, I'm just going to look at a set of focal units' outcomes. And then what I'm going to do is I'm going to hold fixed the treatment assignments of my focal units. So if I'm studying the people at this table, I am not going to do, and when I do my permutations, I'm not going to permute you treatment assignments, because I think the treatment assignment actually has an effect on your outcome. So if I want to know what your outcome would have been if I changed your friend's treatment status, I need to hold fixed your own treatment status. So what I'm going to do is I'm going to do this permutation test, but I'm only going to allow the treatment assignments of the non-focal units to vary. Then I'm going to compute my test statistic, and I will get an exact confidence interval for this hypothesis, an exact p-value for this hypothesis. Okay, so that's the idea for friends. Now, it might still seem that this is very special, and so what's I think non-obvious is then how to take this even further. How can I do this for any type of null hypothesis? So I guess this doesn't quite fit on the slide, apologies, but I think most of the relevant information is there. So here's a network, and now what I want to do is I want to try to test that friends of friends have an effect. Okay, how can I test that friends of friends have an effect? Well, what I need to do is under my null, I can predict your outcome I can say your outcome won't change as long as your treatment status doesn't change and as long as your friend's treatment status don't change. But my model says if your friends of friends treatment status changes, your outcome won't change. That's my null. Friends of friends don't matter. And so what I can do is I can start now, I have this whole network, but I'm only going to analyze 2 guys in this network. Luckily, if you have Facebook data, taking a small set is fine. So I'm only going to analyze 2 guys. And I'm going to hold their treatment status fixed. But furthermore, for each focal guy, I'm going to look at his friends, these brown guys. And the focal guy's friends are going to be what I call buffer units. So I'm not going to change their outcomes either. And so then only the guys who are friends of focal units and are not friends of any focal unit are going to be the people that I randomize. So then I'm going to get this set of treatment assignments, and I'll randomize over those treatment assignments where I'm only randomizing over the treatments of C, D, F, and G. And then I can get an exact p-value for the hypothesis that friends of friends don't matter. Okay. So to make this very general, when we first wrote the paper, actually, we had like sort of a separate approach for each individual hypothesis, and then we came up with I think, an elegant general formulation that captures any hypothesis of this type. So the approach is basically you just define focal units, and then we define what we call level sets of treatment assignment vectors, such that under the null, the outcomes of the focal units are unaffected by which vector in the set is chosen. So these are and this is the intersection of the level sets of A and B. So generally, for each unit, there'll be a level set. There'll be a set of vectors for which, under the null, I know what your outcome is for any of them. And then I take the intersection of those over all the focal units, and I use randomization inference to construct p-values. So just to show how this gets used, I'm actually not an author on this paper, but my co-authors went and analyzed this Facebook voting thing. And they tried to understand, now doing the inference properly, what's the effect of peers. And so what they found, first of all, in the Facebook experiment, they actually only could match up to voting records for 10% of users, so they just made all of those users the focal units. So they actually didn't have to throw away any data. Those were the focal guys. Then they ran a regression of your voting on the peers, and that was their test statistic. Then what they found was an increase in the number of the friends with the banner cause voting. Every person directly induced to vote, 2 friends were induced to vote, which is very strong evidence of peer effects. And this is what the randomization distribution looks like, and here's their observed outcome. So they get very strong evidence and a very conclusive evidence from this. So overall, just to conclude, this is an approach that allows you to test hypotheses without making any assumptions about the structure of your network, the size of your network, the correlation among your network, and how your network grows, and actually have like a perfectly valid test for a very sharp, for a sharp null. And actually, the set of sharp nulls is much, much bigger than you thought. So I think that should be a first step in any experimental design. Now, it's not going to be the full answer, because if you get a huge effect, then you want to get confidence intervals around this estimate, and that we haven't provided. But as a first step, you can be damn sure you haven't got a 0. And isn't that what we all care about, to get published? OK, so thanks very much.
We can take a question for Susan. Oh, yes,
Yeah,
Eric.
Fascinating stuff. Can you say a little bit more about how you pick focal units, and in particular, I mean, matches with voting records doesn't necessarily sound like it would be random, but how much of an effect might that have?
So actually, given the selection of focal units, I can get an exact p-value, and so it would just be a matter of external validity, like whether you think that this result generalizes. So I would have the right p-value for that group, and then you just argue about whether that's an interesting group. Actually, you could do heterogeneous treatment effect estimation using my other papers to see if it varies with covariates, which would help you understand whether it extends. But generally, we don't have a formal mathematical theory of how to choose the focal units, but in the paper, we talk about how the intuition, and we propose a couple of methods. So essentially, like in the Friends of Friends example, it'd be really wasteful to have focal units in such a way that like their friends cancel out everybody else's auxiliary units. So you kind of want them to be distinct from each other in the network, and we proposed some algorithms from computer science for going through the network and figuring out, how to do that.
Awesome. Next up is Eric.
So I'm going to turn to the motivating application of healthcare and talk about the challenge of mining the web or harnessing web behavioral data as a sensor array for some challenging healthcare problems. Our team has done quite a bit of work in epidemiology, diagnosis, characterizing phases of illness, and looking at medications from web data. We found that at Bing search in our logs, about 10% of queries are health-related. Google has reported about the same kind of percentages. Pew showed a quite heavy weighting towards healthcare in terms of the web being kind of the oracle to address anxieties and information about health challenges. One can imagine doing a number of interesting things in healthcare. We found that there's some opportunities to understand the noisy data and to regularize it with sensor error models, generate models of users and how they report on detecting rare outcomes. One interesting construct that anybody looking at the web for health information, whether it be for tracking influenza, for example, as made famous by the Google flu trends a number of years back, or other work, is discriminating experiential behaviors. Users who are searching because they themselves have an illness versus exploratory search. And a lot of the big wins in recent years by several teams involve developing statistical classifiers for, is this behavior you're seeing coming from somebody who actually has an illness, disease, or actual question about symptomatology versus is this exploration? Lots of work going on in that space, and it's very promising. I wanted to talk about adverse drug reactions. It's a really interesting challenge problem. Thousands of deaths in the US alone per year. Actually, some estimates go into the hundreds of billions of dollars of cost associated with the people with this problem, including the people who live through these incidents. Sometimes the death, unfortunately, are the lesser expensive cases. But we found in our logs that about 1 in 250 people are querying on one of the top 100 drugs. It's quite an interesting set of possibilities for sensing. Pharmacovigilance is the word used to refer to the processes of post-market safety monitoring. In creating medication, there's a set of phases. You can read about these phases going to approval. But of course, when a medication goes into the real world, you now in the open world face issues of combinations of drugs, all sorts of unexplored parts of physiology that weren't part of the preclinical to phase 3 of drug trials. And so what is put in place in several countries, like the United States, are spontaneous reporting systems. And spontaneous reporting systems have been a focus of attention for statistical analysis. Like, what does it mean when you have numerators and you have uncertain denominators, for example, in these outcomes? So the FDA in the US has the AIRS, or the Adverse Event Reporting System. Every year, about 250,000 reports come in on 15,000 drugs. There are some high-profile cases. Some are cut off here, but of course, everyone knows the Vioxx case a few years ago. This was a post-market surveillance challenge that led to all sorts of controversy as to who knew what when. The current way things work is that physicians typically and other professionals will fill out paper forms. There's also an online version of this on a per-patient basis or a per-adverse event basis. Kind of a slow process, a tedious process, and there's the possibility that the web will give us a lot more. So about 5 years ago, I was talking to Russ Altman at Stanford Biomedical Informatics, and he and a student, Nick Tatanetti, had just discovered, looking at AIRS data, through some analyses, that patients who seemed to take 2 drugs, Paxil, an antidepressant, an anti-anxiety drug, and a common statin, Provocol, seemed to be having hyperglycemia with a higher likelihood than background. But each drug separately was not leading to this effect. So it was a combination effect, and we see this all the time in healthcare. This was a previously a noticed effect. We thought we'd turn to the web as a sensor and see what we might find. The results had not been published yet on their findings. We actually created a set of synonyms, kinds of user-centric words that might be used to refer to various subjective experiences with hyperglycemia. Did a two-step random walk process to generate sets of synonyms for these words as well, and found out with looking at 12 months of logs, about 6 million people, there were 82 million drug symptom condition queries, and looked at drug pairs and where they occurred. In doing this, we found that if you look at basically people who were searching on just paroxetine versus people searching on pravastatin, how often they would use one of these terms that would link to the hyperglycemia state versus both, and looking at also background. And so basically what we're doing here is we're doing what's very common in the pharmacovigilance space. We're computing what's called disproportionality analysis with a reporting ratio, looking at people who search on paroxetine alone, pravastatin alone, and hyperglycemic-related terms. I think we've lost now our ability to go forward here. So I have to have my, there we go. Oh, now we're going too fast here. Okay, bring me back a little bit now. There we go. Stop right here. I may have to guide this locomotive the whole way through now. So basically we're computing, we're looking at the statistic of people who search on both drugs and hypoglycemic symptomatology, and people who search on each one. You see below here what's called the reporting ratio, and how we see over-reporting of people who are searching on both drug of a hypoglycemic effect. Now, what we did was is wanted to understand and characterize the web as a sensor for these drug interactions. So what we did was we went back to the literature and found 62 pairs of drugs that had been analyzed very, very carefully. 31 are known true positives for hypoglycemic reaction, and the other 31 are confirmed as negative through clinical trials. And by basically taking these known, this gold standard data set, and our approach, in this case, the reporting ratio approach, and scanning through that parameter, we can generate ROC curves to show how well we can detect these with all of our features, or just some we call hyperglycemia-focused features, some of the stronger features. And it's interesting, so we're looking at basically how well we can detect a set of true positives and true negatives to characterize the web with our methodology as acting as an actual sensor array. We also can look at what features, what kinds of features, these are basically categories, of course they each lead to a shower of synonyms, are actually helping to basically contribute to the ROC curve area under the curve. Now, once we had this original work done, we started looking at different models, and of course the pharmacovigilance literature is filled with alternate models for how people look at spontaneous reports and conversations about them, which are better. We started generating some of our own for looking at, for example, the independent influence model and what score we would expect with this model, with causal independence assumed versus other models. And we started putting these models into a tool. We call this, so remember the FDA's tool is called AIRS. We call this behavioral log-based adverse event reporting system, or BLAIRS. We have a very cute logo. What we do is we generate in the system a background symptom spectra across what's called the Merck symptoms, that's standard ontology of symptomatology. And then a tool lets us take, for example, looking at drug interactions, a matrix of all drugs by all drugs, and for the metric we pick, will pop out and show us interesting interactions. So, for example, we want to go here to the corner here and look at the interaction of Claritin and Adipex over expectation. And we can see in this visualization kind of an interactive tool, so it's like a toolkit now. Symptoms across the top, where we might see interesting over-reporting. In this case, we see it's with fainting or syncope. Here's Protonex, a common proton pump inhibitor. I'm just going to ask you to raise your hands taking this drug. Very common, though, and Coumadin. But you see here, we see rash popping up. These are interesting interactive tools working with the web as back end. Now that I've introduced you to a basic study, I want to take you through a more serious analysis. I say more serious because There are some serious rare side effects. We got to get into now the statistics of rarity. A data workload called OMOP, Observational Medical Outcomes Partnership, was created several years ago, looking at 181 drugs with a true positive and true negative gold standard on 4 outcomes of concern. Very severe outcomes: heart attack, renal failure, acute liver injury, upper GI bleeding. These are considered the most significant drug safety outcomes that what we all worry about in the world, people in this field. So we had 18 months of internet logs, 2 years here, 80 million users captured with a web browser add-on, looking at Google, Bing, and Yahoo search, and we had an anonymous identifier for that captured the instance of the browser. The trial design is, we call it a self-control design. Each searcher serves as their own control across the transom of an event we're looking for, and then downstream symptoms and condition searches. We defined the notion of a query rate ratio, and this is the number of queries we see in an observation period, in this case 60 days, before and after a sentinel event with an exclusion period. Now, this gives you a sense for actually we're designing, in some ways, clinical trials with web data now. So basically saying, well, here's where a drug search first appeared in our logs, user sub I, and then we're going to watch until that drug search disappears, because we don't want to have any confounding people searching on web pages that are related. And we have a certain exclusion period going up until this alpha, which is the last drug query. And then we have a beta exclusion period of 7 days. And then after that period, we begin observing for 60 days after and symmetrically before to calculate our query rate ratios before and after. And then basically for each user, we're going to do the same thing, the same kind of parameterization of the search logs. And then we want to sort of take our events now and then look at how we can understand rare events in a big sea of noisy data. The problem with these kinds of events, and this has been noticed by the FDA many years ago and became part of their standards of practice, is that there's high sampling variability when both the baseline and observed frequencies are very small. So it might turn out that when you get your pack of your medications and you see, oh, there's a concern of heart attack, it's considered very, very small, 1 in 100,000. But we still care about that and want to know, is the drug causing that effect, or is it just baseline? Will I just be at baseline, especially when the FDA is making decisions about box labeling changes and updates, for example. So we turn to empirical Bayesian method. You can look at this as a two-hierarchy Bayesian method. And the idea is you come up with you assume your observed counts, what you're seeing is drawn from a Poisson distribution with an unknown mean, and you're going to basically, at the same time as getting counts, inferring what the means are of these Poisson distributions. And I refer people here, if you're interested in this methodology, to the multi-item gamma Poisson shrinker. It's a fancy multi-word description of a method by Dumarchal and Pregobon, but this method became standard of practice for the FDA now in how they look at errors data. So we wanted to just talk to the FDA, use these same methods. They're well motivated, and they're interesting to see how they work. But let me show you the results here, because they're kind of exciting, I think. So the blue are ROC curves generated from the web data, and we show a curve in blue for acute renal failure, upper GI bleed, heart attack, and liver injury for the OMAP workload, which is a standard right now. Can you sort of figure this out from a sensor set of signals from somewhere? Traditionally, it's been errors data, and we're showing how well we do with the web data. And you see the red is the errors data. So the curves are interestingly a little bit different in structure and shape. And you see here, I'm listing out the errors in the search area into the curves here. And now I'm going to say, you can read in our paper at Nature CPT how we can combine these together and do better together. So this is what interests the FDA. In fact, I'll be at an Institute of Medicine study on Tuesday in DC, presenting a more technical version of this talk to the FDA folks and other people doing regulatory science advances in a workshop in that space. Now, just to mention what gets me very excited and where we're going next with this is bridging the online world to traditional health data. You saw we did it a little bit right now with AIRS, if you consider that traditional health. But I mean actually hospital data, clinical trials. How do we bridge the two to really learn to have some ground truth, for example? In many areas, we don't have that kind of ground truth. And so we've developed a method that lets us link medical studies to the web through a methodology where web people who are part of the IRB study can get onto a web page from the browser they usually use and click a survey, click a button, and send us in Bing logs their browser code and get checked into the study now. We get 18 months back of all their data and can go forward with them for doing studies. And we're working in breast cancer, as you can see right now, among other studies. I'll just mention one, I'll just leave one slide which got me very excited several years ago about the prospects of linking the messy, noisy, crazily big world of the sense data on the web, behavioral data, with traditional health data, small, curated, expensive, with just one result. Again, this is published several years ago. Robert West, an intern with me, one of your Lescovitz students, was interested in nutrition on the web, and he basically looked at characterizing the ingredients in downloaded recipes around the world. Salt, cholesterol, fat. It's incredible how these correlate with all sorts of health effects and obesity around the world and sort of CDC statistics. But I was very interested in looking at Washington, D.C. area, where I'll be showing this slide next week, D.C. metro area, looking at salt content over time in downloaded recipes for this whole metro area. Well, it turns out that there's been a theory for many years that people with congestive heart failure get off their diet around holiday times, eat salty meals during festive gatherings, and become liquid overloaded and hard of breathing and come into emergency rooms. They call this holiday heart. Well, this just shows you here the admissions at the largest urban hospital emergency department in the DC area in black, and the average sodium per serving in the meals being downloaded in the DC, or all across the DC area, seen through our logs. Again, this is just one point. We want to do more work in making these links. We think there's lots of possibility here, again, with regularizing what seems like a stream of noise in a very large sensor array into a well-characterized sensor error model, and then leveraging this to push ahead with public health and more general health care. So I'll stop there.
Awesome. So I would invite Sendhil and Susan to come up with Eric to be up here on the panel. And we can take a question for Eric while everybody's getting settled, if there's any clarifying questions. Let me just give you a little bit of the ground rules, right? Obviously, we now have a serious amount of time for conversation. We have 2 mics in the room. Susan has one of them in her hand, and then there's another one right over here. So anybody who is interested in asking a question, just raise your hand, and I'll sort of get an order of questions to come, saying, you know, this person, then this person, then this person. Then Susan will bring over a microphone, and you can ask your question directly. I'll take the liberty of being the session chair to maybe start the questioning off. It seems to me that there is a tremendous amount of overlap in these in the sort of unobserved structure of these 3 talks around sampling variability. Eric certainly mentioned it, and I think the importance of it to both Sendhil and Susan's talks are relatively obvious. So my question is really for Sendhil and Susan, but I think Eric could have a lot to say about this. So Sendhil, how worried are we that the benchmarks that are created by machine learning in the cases that you're talking about are finding structure not in the data generating process per se, but rather in the specific data generated by that sample of people giving answers to a survey? And sort of similarly, Susan, you know, typically we don't have a whole network. We have some sample of the network. What are some of the concerns you have about how the expected p-values or the exact p-values might behave given that we have missing or incomplete data about the network?
Why don't you go first?
I think that notion, I guess I'd put it in the machine learning context as transfer learning. And I think the implicit hypothesis that people have is that theories transfer better than sort of black box machine learning models. And I think it would actually be super interesting to test that. And so I was shocked in our context that this black box table lookup transfers from people making up coins on Mechanical Turk to this loan officer data set. It's just, that was shocking to me, but that doesn't mean it's going to happen in many places. I think it would just be super interesting to explore that question, because I think we have this bias that our theories are somehow more robust, and I don't know if that's true. It'd be useful to know.
Good. So I guess the easier answer is that, in fact, this sort of how well do we measure the network is actually one of, I think, a leading application of our methodology. So one of the examples I didn't have time to go through in depth that fits into our framework is network sparsification. I mentioned it, that weak ties don't matter, but strong ties do matter. So I can construct a bunch of alternative definitions of the network. What is a tie? Is it 15 emails? Is it posting a picture? Is it commenting? What is the actual network definition? And then I can test the hypothesis that the links that I've left out don't matter. And if I can give a nice resounding rejection to that, then I can kind of go work away with my simpler network. And so I would say, of course, that doesn't directly answer your question, but if I had a network and I'm worried about mismeasurement, I can sort of look at rejecting kind of the weakest links in my network, and that'll give me a sense of what would happen if I had added a few links that I had missed.
I guess the question is, what if we have some network and we don't know if it's the network? We don't observe those links that we can cull away or not cull away.
So I think you need more modeling to think about, what exactly. Then you have to start thinking about sampling from a larger network, and you need to define what that means, which is harder. But I would still say that, in some sense, the data you have is the data that you have. You can't, if you absent making up data, thinking about taking a bit of it away is a first
So
pass.
let me make a comment. These kinds of analyses, and especially to your question just now, these days versus the kind of statistics that was done maybe 30 years ago for the problems being looked at in the sample size and the sizes of the ends are much more in the open world, where we can't observe everything. There's extraordinary possibilities about exogenous variables that are having big effects. I tend to get more and more comfortable the more I see analyses that show me the robustness of the results to structural and parameter-centric sensitivity analyses. I want to see sweeps through the parameter space. I want to see robustness of the results. So what happens to the results that I'm going to be publishing as I change the structural model? There are like 2 or 3 competing models in pharmacovigilance. I want to try them all out, and if I get ups and downs, I go, okay, I want to back off now and really think this out, think this clearly. We can always publish papers and say, here are my assumptions, you can check them. Here's my data set, you can check the data set, and here are the results. But I also want to make sure when we write these papers to say, this was very highly sensitive to this variable setting, or highly sensitive to this assumption about the model I was using, and also make sure when it comes to false discovery and so on, that I clearly think about usages. With pharmacovigilance, I've been comfortable because this toolkit, this Blair's toolkit, for example, we say, oh, it's exploratory, and you just get a sense for where you might point your focus of attention for formal clinical trials next. That's also an expensive set of decisions, but the idea of we're not directly saying this is true. We're saying, for now, we're saying focus your attention in this way, here are our assumptions, so thinking about the use case. But false discovery is going to becoming more and more common with our big data sets in the open world.
So can I ask a quick question about that?
Yeah,
I'd love to hear your thoughts on when you say you want to sweep through model space and find robustness. In some sense, what are the different models doing for you? In other words, you want to be robust to them, but so that's almost what they're not doing for you. What's the part that you feel like they're helping you on? You know what I mean? How are they structuring the analysis, or in your example?
These models are all very closely related, but they're slightly they have slightly different motivations, and they're also considered standards of practice by different communities. And so the idea is to actually look at the models. We can critique them and say this is a much better model, the causal independence model, than what was being used or this graphical model that captures dependencies. It really goes much beyond the simple dependence assumptions being made by the FDA, for example. So we can actually critique them, but then we want to actually, for communicability and understandability, use them and express them to the world. But also just want to see if different communities ran my data on their pet models, what they would see and why. If they all point in the same direction, or the weak models point in the same direction as the strong model, then I can sort of calm down a bit and keep my arguments at bay.
So can I just make a comment on what you said as well about the looking at robustness? So this is something that the social sciences, in some sense, have always done, but relatively unsystematically. Social sciences have usually had observational data, therefore needed modeling assumptions to establish causality, like things like independence or independence of an instrument, or they might impose some economic structure like the parametric models that Sendhil had. So we have always published empirical papers that talked a lot about robustness. Like that was a key, that was always the main thing your reviewers complain about and so on. But at the same time, we didn't have very systematic ways to do it. And then if you look over at like machine learning, they're typically more atheoretical models, and so there's not sort of this need to really check assumptions. It's just kind of, did I hit my mean squared error criteria? Did I reduce mean squared error? Because you have this test set that has a ground truth in it. But for a lot of causal questions, you don't know the ground truth. There is no test set with the ground truth. So we don't have the ability to know whether our model's done well. And so we've had more emphasis on robustness. So one of the things that I'm interested in, I wrote a short paper on this in the American Economic Review last January, was trying to combine machine learning methods with econometric models to try to systematically assess robustness, to kind of search through different variants of a model and see whether you're robust. But I think that's really in its infancy and would be an interesting area for future work.
For research. I have to say, as an example, I listened to the first talk, and I sat there thinking, well, boy, as a Bayesian, how would I solve this problem? As a Bayesian, what would I do with the priors on what the human would do versus what the coin would do? Should it be an untested coin as I'm seeing the flips? And I thought, oh, well, of course, the Bayesian approach would be much more powerful than the assumptions you're making, but they'd be sort of rely on my prior distributions and so on, and how I do inferences based on them using a beta distribution that's updated, for example. And I sat there thinking, I want to try that out. I want to try that out and go to your office and sit with you and try my model versus your model, and then look at these different approaches to this problem. And this kind of dialogue is very powerful and useful in establishing robustness as part of conversations about how we do modeling.
So maybe another comment on Sendhil's paper, which I thought was really interesting, was he was really highlighting kind of using a model to create the features for a machine learning model. So using a theory model, an economic theory model, to motivate what features went into the machine learning model. And that was really exciting for me to see, because I've over the years had a lot of arguments with the machine learning side about whether that kind of exercise is useful. Because I think if you're thinking of a world with a big data setting, and I've got a great machine, and my machine is going to figure out all the important interactions and the variables, and it's bad to kind of impose some structure on it. Like I should let the data speak, and the more I let my data speak without interfering with it, the better. But yet, when you actually look at the statistical properties of these things, no data set is actually big enough. In my research now, I'm doing asymptotic normality and everything, but when you need, actually, if you have a lot of covariates, you need trillions, quadrillions of observations to really fully understand what's in your data. And so I think an underappreciated thing is how useful and how much more statistical power you can get when theory guides your feature creation and you sort of help your model find what's interesting, because it's actually very, very expensive in terms of data to just discover a four-way interaction with a certain functional form. So I really like that aspect of what you're showing and how you show that the machine learning on top of the features created by economic theory is so powerful.
So we can turn to the audience for questions. There's a question here and then just behind. You can come get the mic and then Susan will help you afterwards.
Hello? Is that good?
Is that on?
Cool.
Great.
Yeah.
Okay. Thanks for the talk. I really enjoyed them. And full disclosure, my background is in machine learning and discovery of things. So, my question actually is more focused toward the social scientists, sort of the Sendhil and Susan, because your domains your problem domains I think are very interesting. But there seems to be this notion when you use machine learning, it's very good at prediction, very good at classification, and so you're letting you're basically using machine learning to test your hypotheses out. Is there any interest, and you mentioned this actually quite recently, Susan, about sort of joining machine learning econometrics, where you let machine learning discover things, right? So instead of simply just saying, okay, here's my theory, here's what I think, here's the effect I think, what's machine learning saying the effect is? What is it saying that the difference is? Can we actually discover the places or the locations or the set of features that give us sort of the largest effect or the smallest effects or some kind of interesting effects? So that's what I want to do, and so I was curious to know what you guys think about sort of that problem.
I think that Susan's done a lot of work on the causal inference aspect of discovery.
Sure.
But even if we just take a step back, I mean, I think that one of the most challenging things that I've encountered in wrestling with that problem that you're describing is, let's take like the association rules literature.
Sure.
And the truth is, when we look at the association rules, we have these celebrated successes where we look at them and go, wow, what a cool discovery. But almost all of what they discover, you look at it and go either, I guess that's obvious, or, what's that? Oh well, must be a weird thing. So there's some interface problem, which is what I thought made your discovery thing so interesting, is there's some interface problem that when we do either unsupervised learning or supervised learning to like look at which variables matter, some human interface problem, because usually the discovery problem is one where we hope to discover something that to us in our heads, with the models latent in our backgrounds, make us say, oh, that's interesting. That's the aha moment we want. So this is not just a statistical problem of discovery,
Sure.
but some statistical problem combined with some behavioral issue of what is it that relative, so in other words, even if I was doing discovery, I think I would want to get more precise about what are the latent intuitions I have so that I kind of am able to ask what is new in the data orthogonalized against my intuitions. So, and I think that's been the challenge, at least when trying to do that I've discovered.
So just to comment, I mean, actually, a shorter answer on Sendhil's behalf is that when he took these economic features and put them into his lasso model,
Sure.
the variables that were selected discovered interactions and nonlinearities that weren't in the economic theory.
Sure.
So go Sendhil. Then from my perspective, one of the I've been working on using machine learning methods to discover subgroups with heterogeneous treatment effects.
Yeah.
As well as to flesh out the entire non-parametric surface of treatment effects in experiments or observational studies. So I'm starting from the perspective, suppose, like the people in this room, you actually ran a randomized experiment,
Sure.
and so you've got actually a notion of a cause and effect. You know, you've got a treatment. Now I want to tailor my machine learning methods to determine who had a high treatment and who had a low treatment. So in a medical study, I could try to see. I was just trying to think if I could apply it to your data. You know, which types of people tend to have that interaction, and which types of people don't. Or in my Facebook study, I could say, all right, yes, the people whose voting records I matched are not random, but I can discover the heterogeneous treatment effect as a function of all the things I observe about the people, and then I can match that up with the general population to reweight my results. So this type of thing is, I think, you know, really, really promising. Of course, I'm excited about it. One of the big gaps was that you couldn't do valid statistical inference afterwards. If I bothered running an experiment, I probably wanted to test a hypothesis and do valid statistical inference.
Yeah.
And so what I've been working on is the underlying statistical theory that will allow you to do that valid inference after you've done that exploration. So not just find something weird in the data, but put a confidence interval around it that you could publish in a scientific journal.
I think I should also point out that, so a lot of what you'll be hearing about the next 2 days is we have this data, here's how we collected it, and here's our study of it, and here are our results. But we want to keep in mind, and this whole group should take this very seriously, and my co-panelists here, that we can take our methods, our best methods that we have for doing inference and drawing conclusions and building insights, and turn it around coherently and drive volume information computations to say, here's a big pool of data, what more do I gather now? This is especially critical in healthcare, right? This could be expensive data. But we could take our model and our causal reasoning metrics, for example, and what our inference is, and say, what more data would I collect to discriminate now? Or even, what clinical trial would I pay for right now on top of what I already know? And we tend in this room to take our data and say, let's play with it, versus we're in the open world, we have data streams now, we can collect more data.
Just to follow up on those first two answers, so it seemed to me, Sendhil,
I'm
that
left out continually around here.
only by me, unfortunately. Sendhil, you seem to be saying, I want to discover things, but I want to discover something that is sort of meaningful given what I know or think beforehand, so that I can say, oh, that which popped out is somehow novel and interesting given something that I already knew. And when we traditionally think about heterogeneous treatment effects, we think about, okay, well, I have some ideas about what subsets of the population may matter, men versus women or people of a certain age. So what happens when something pops out, a particular subset of the graph that we can't make meaning around in terms of they behave differently for some latent unobserved reason, but it doesn't map to anything we know or understand? And
But let's say it in the positive way. I thought Eric's point was exactly right. The reason we care about discovery is that everything we've built, every theory or every model we've built is built on the things we've chosen to measure. The things we've chosen to measure are the things that our theories or our intuitions tell us matter. So one reason it's very important to discover and change our intuitions, then changes what we will then measure next. And so in some sense, there is, no matter how good you think your model is, it is constrained, I thought that was exactly right, it's constrained by what's measured. It cannot look at disease that are unobservable. But some things that are unobserved are not unobservable, they can be measured. And so to me, the positive statement here is how do you create that loop so that our understanding, so it doesn't have to be that I need to look at this interaction term in a causal inference thing or a variable in a predictive model and say, oh, I know what that is. It can be enough that you say, with some guesses, I have a sense as to what that is. Let me go and measure that, add that to my data, and see how much it helps. I mean, if you look at the arc of science, it's always been new data leads to a guess, leads to new measurement. And I think that angle, increasing the width of our data, is, I think, exactly where understanding matters.
And wouldn't it be nice, even though your question over here, wouldn't it be nice if when a paper is written, there was more of a formal and detailed, expected way people talk about why they collected this data, what their initial intuitions were, because that's actually very important in the statistical analysis of where they're going with the data and their analyses.
It was, so I mean, in drug discovery, and actually in development economics experiments in economics and so on, people put up a pre-analysis plan to try to get around the problem of multiple testing, which I think is super important, and multiple testing is a huge problem. But yet it's also very limiting, because how could I possibly have theories about, 1,000 covariates I could put together from your past browsing history and so on. And so I think what's been bad about a lot of small data analysis and social science research in the past is that we try to look for robustness, and so we're diligently testing. Along the way of looking for robustness, we discover something, and of course we only report and publish the kind of interesting things we discovered, and of course we put down the ones that are especially bad, and so you have this non-systematic result, which is why all the results are overstated. And so what I think the power of machine learning is that it's a systematic mapping from here's my data, the data goes in, the machine does the discovery, and out come the results. And you can see within the context of this method, of course you can shop for methods, but within the context of this method, it's very reproducible, the entire discovery process. And so that's one of the reasons I got so excited about it and tried to then further develop it for statistical inference, was that it kind of solves that problem, at least to the extent that fishing for methods is always a problem. But once you're in the method, you know that what is this little weird thing that I found, I can put a confidence interval around it, including the multiple testing that went into it.
We won't mention the people that try out N machine learning algorithms.
Exactly. Yes, that never happens.
I just wanted to add a little bit to that, and then I'll sit down, I promise. So Susie made a comment about the goal of estimating the entire surface, right?
Yeah.
Which I think is one thing machine learning is very good at. I think the question that I'm really intrigued by, or you know, want to get you guys' opinion on is, once you've estimated the entire surface, right, and you can imagine every part of the surface being represented by some subpopulation, how do you identify, how do you search for the entire space, right? The 2 to the whatever, 2 to 10, 2 to the 300 subpopulations that actually have that effect, right? You can model it and you can sort of say, now my algorithm, I want to know what the effect is for, you know, 20-year-old black men who are left-handed, but then how do you figure out it's, you know, 30-year-old white women who are right-handed who actually have the large effect? And that space is really large, so how do you actually like find the thing? I'm hoping to find the thing, but like, so is there interest in actually being able to find the thing? And I think it speaks to your point of, well, we find it, but what do we do with it? And I think that sort of is the next step after you've actually found it, right? You can rerun experiments maybe if they're digital and try to understand the mechanism behind it. The point is I think you need to find the actual group where the mechanism is at play before you can find the mechanism. So I'll sit down, but that was sort of my follow-up to that conversation.
Yeah, so I'd say, like, I actually have these 2 papers right now, and it's really interesting the different responses I get to them. So one of them I presented last year in an early form about finding subpopulations. So it's basically like it uses recursive partitioning to find subgroups with heterogeneous treatment effects. And then the other one is a random forest method that finds the whole surface. And some people are like, oh, why would you ever do that stupid subgroup stuff? Like, of course, the random forest is the best possible thing. And then other people are like, oh, that random forest, like, what the hell you do with that? Like, it's just a huge surface, and unless you do something else to it, it couldn't possibly be useful or interpretable. So I love your subgroup stuff because that actually gives me something I can interpret and is actionable. A few people like both, but hopefully I can find referees who like each. But it's actually, I think, for different purposes, each of these different types of things is useful. When I've looked at the whole surface, though, you're right, you then have to model on top of it. And I can say, okay, who has the highest statistically significant, in which dimension is the highest statistically significant slope, where are the most, the biggest interaction effects, and I can sort of search my space, but I have to do sort of additional processing on that. It fits great, but if you actually want to use it, then you need to understand, you need to have a way to actually incorporate all of that rich information. So it's like a model that then needs to be modeled again, and if you put some sort of economic theory or domain-specific theory on top of it, I think it becomes much more interesting, coming back to like test hypotheses and so on.
Thanks.
Thanks. 3 very good talks. Lucas Samir, I work for Booking.com. I must say, Susan, as a machine learner, I think the machine learning community has way too much emphasis on mean squared error and not enough on robustness. So I want to support that. I have a question about your talk at the end. You mentioned for those focal units, you have different ways of selecting them. And the thing you mentioned is you look at things that are far apart in the network because you don't want too much overlap. Have you looked at what effect these selection methods for the focal units has on the overall result? Because I can imagine that if you have a network that has many central units, your method has less opportunity to select those central units, and those central units might actually be different in behavior than all the others. So if you have a method that selects things that are on the outside of the network, that might change the end result.
Yeah, so welcome to the life of running network experiments. So for just more broadly, like there's a whole literature of trying to find subgroups and treat the subgroups and have control subgroups. Almost anything you do does potentially have these kinds of selection concerns. To get valid statistical inference, what you always want to do is first create a potential target population and then randomly treat once you've identified the population. So in that sense, we're not making a statistical error. But there's a question of generalizability and whether you've actually covered the whole network.
Whether the sample is representative.
Exactly. And so I think there you can, what I have found in my empirical applications of this is that we often, like in applications, actually like make a graph, and there's sort of like coverage and representativeness versus statistical power and sort of cleanness of the statistical analysis. And depending on the type of experiment you're running, that's going to have different concerns. But there's almost always like a frontier. Like the thing that's the most generalizable and most complete might have less statistical power. So I don't know, Dean Eccles, my co-author, is in the audience, and he's done a lot of that too. Dean, do you have any, or Eitan, any comments on that?
Yeah, I guess the only other comment is just that if you reject the null of those spillovers, it doesn't actually matter just rejected the null. Your null was a sharp null hypothesis that these don't matter. So if you did succeed in rejecting the null, you might not believe your point estimate, but you should go on to then model those peer effects and care about those peer effects in a more systematic way. Now, what I think is the more legitimate worry is that you might end up selecting focal units in a way that for particular alternatives gives you less power than you'd like. So if it turns out that these central units are the ones who are really affected by their friends, and you chose as focal units all the peripheral units, and there are no peer effects for them, then that's where you could get into a challenge. But if you do successfully reject, then you know that something's going on, and you might want to go on to model it.
Right, so you're not actually trying to estimate the size of the effect here, just whether the effect is there or not.
Right, or at least that's what we can do statistical inference for, yeah.
Thanks.
David? Might want to pass the mic this way, or not.
Hi,
David.
those were great talks. I'm wondering the following. So as I hear Sendhil talk and then I hear Eric talk, so essentially Sendhil, you're kind of looking to bring the theories from social sciences somehow together with what's going on in machine learning. You're using machine learning to get bounds on what the theories might do. You'd like to maybe loop that in more closely and actually take ideas out of the learning algorithms into the theory. And as I heard Eric talking and kind of emphasizing the blends between the policies that are out there and what the machine learning models are telling you, kind of what I'm wondering is, what more work should we be doing in making our machine learning models kind of more responsive to things that would be useful for us as scientists, or us as policymakers, or us just as humans trying to understand the world around us? We do hear people, so Cynthia Rudin, for example, has worked a lot on interpretability of models, and I think even she gave a talk on that here last year. But just wanted to get your thoughts on that, and wondering if the community here might be the right people to think more broadly about this.
Yeah, no, it's a really great question, David. You know, there's some really great work over the years in both on both the inference side and on the machine learning side in making those processes more understandable for communicability and interpretability. Rich Caruana and others have done such a really nice work in looking at generalized linear models with shaping procedures that take complex nonlinear machine learning and splaying out a linear equation, linear additive model with functions that describe, for example, pairwise interactions at the end, or triplets, after they cover the main effects as just a sum with functions. And I found that work and without losing much power. And I found that work being interesting because you can then talk to a policymaker about the contributing variables and be making sense. Same for inferential procedures. There's understandable and less understandable inference procedures you can talk to folks about. The European community actually on their privacy policies are generating kind of approaches where they say, it's okay to do machine learning as a company, but you have to explain the procedure to the masses, explain what's going on to consumers. And I think, oh my gosh, I mean, with these multi-level cascades called deep learning, layered logistic regressions called deep learning, even the engineers don't know really what's going on. They're trying to grapple with heat maps, for example, at different layers. And so there might be some actually true policy issues coming up in a dialogue between understandability, interpretability, and even law.
So let me start off on that, but something that seems like a tangent. There's a Borges short story where he has this beautiful paragraph where he talks about this country with cartographers who are so into maps that they build these beautiful maps, and the field gets more and more into the maps until they build the greatest of all maps of this country, which is a third of the size of the country itself. And there's something interesting about that, I think, actually, for what we do and what these models do. We typically have used models that when we found predictable structure, that predictable structure is much simpler than the thing we're modeling. That's the whole point. And then it sits in our heads. Now we're in a funny position because we have predictable structure, and take a deep learning thing, which is not noise, it's not sampling, it is the predictable structure. We can use it to predict the world. but it's like a map a third of the size of the country. It doesn't fit in our heads. It doesn't do anything. And so I think that, to me, I guess, to David, to your question, what can the community do? I think that, like Cynthia Rudin is doing, I actually think there's a huge amount of return to tackling the interpretability question, but not wholesale, at least in my mind, in actually asking, what is the productive value of interpretability? Not taking interpretability as a pure outcome in and of itself. For example, I've done behavioral science. I'm not sure that if my only goal were to create adoption by policymakers, I would in any way make the models more interpretable. I think people are much more used to process and explaining to them, this is the process we undertook, this is how we did it, this is what we did, this is what we tested. And look, no doctor understands what goes into the actual chemistry of a prostate exam. I mean, not no doctor, but they know there are these 32 data points, some chemistry goes in the back and it comes back with numbers. They just know that there's a process that does that translation. So to me, interpretability is going to have to come back to, what are you going to use the interpretability for? And if we can model that, then we can give back to the algorithm and say, well, this is the thing you want to maximize. To the earlier question, for example, one thing you could use interpretability for is because you want to use interpretability to identify interpretable subgroups. But interpretable subgroups, that's great. You don't need to interpret the entire damn model. You're like almost saying, give me an interpretable nugget, like one. I'll live with one. And so I think that as we start to pen that problem in, at least that's the way I would try and pen that in.
So let me jump in on this. So I spent a number of years of my life working in a literature in economics called sort of structural economic modeling. And in that literature, you actually write down pretty fully like what people's preferences are with a functional form or perhaps in a semi-parametric way. And then you estimate the model and you use it to do counterfactuals. So this is the state of the art, like if the Department of Justice wants to block a merger, they're going to do a counterfactual model of how the prices would change and so on. So it's a decades-old literature, very huge literature. And so in this literature, because you're writing down these obviously wrong assumptions in the sense that everybody's maximizing profits and this is the functional form of their profit function and so on, there's a lot of sort of latent understanding and art about how you do this well. And so one of the, like a comment in a seminar on a paper like this would be, okay, I don't like these 5 assumptions that you're making, like the errors are normally distributed or this or that, but tell me the counterfactual you're going to use the model for, and that will focus my attention on whether that assumption matters and what's important. And so just for example, like if you're trying to block a merger, it's really important that you understand how price-sensitive consumers are and how close substitute the products are. And so there's some things about your modeling that really affect your measures of how substitutable the products are. And so people pay a lot of attention to those assumptions and not so much to the other assumptions. But sort of the state of the art that we're teaching our first-year graduate students is, before you decide if you have a good model or if you have good assumptions or whatever, all those choices should be driven by the kind of counterfactual you want to do. So in the randomized experiment world, we have kind of treatment and control, so the counterfactual is, what if we gave everybody the treatment? That's kind of obvious. But in some of these more complicated settings, you're doing more complicated counterfactuals. And I find that that kind of way of thinking is almost entirely absent from the machine learning kind of side of things, because they're just not used to thinking about, the counterfactual is the test set, not the counterfactual is some other world. So Leon Batu is going to talk a bit about that later today, and he has some applications of there, but mostly, that's been the domain of this particular subfield of economics.
And we shouldn't leave out of this discussion the importance of understandability and in building insights for the researchers themselves as they do their own gradient descent or pop through spaces of what they're going to do next. I happen to say, when I have a big data set, I know I might end up choosing the best method per performance and so on, but I love the idea of taking an analysis of Bayesian structure search to sort of generate me the probabilistic graph. I want to see even if it's a myopic search, what the models come up with and what nodes are talking to what nodes in the random variable tapestry. So I think it's just to help me understand what's going on from the point of view of the assumptions made by the graphical search procedure.
It's a fascinating epistemological discussion here on this. And I want to ask a question that sort of goes back to something that you said, Susan, about using a machine learning capability to do feature extraction on this. I'm sort of curious about, and I want to try to connect this with your comment on the medical self-reporting. I'm interested in the ontology of features. You know, I'm not well, am I queasy, achy, etc. There's certain semantics associated with this. And I'm sort of, and you can do the same thing in economics, how innovative the organization, we were discussing in the back, data-driven the organization is. So what I'm curious about is, where have you seen interesting work done in machine learning to train around ontologies, either in an aggregating, synthesizing way, or in a deconstructive sort of way, so we can see, you know, which sub-attributes drive robustness and sensitivity, or which collection of anti-reductionist on that. So have you seen interesting things, or are you doing interesting things in that?
I mean, many places. Speaking of prostate, we have a paper out.
Who doesn't want to speak about prostate?
Over the last few months, looking at anonymized logs, but for how people who clearly have just been given a diagnosis of prostate cancer do decision-making using the web as a decision support system. And we actually did generate an ontology of symptomatology there, and it was very valuable. And you can read about the ontology and how we use that to understand what goes on in the minds of, we think, folks who are grappling to know better about what to do next in a situation where it's not cookie cutter like some other diagnoses. A lot of preference-related kinds of things that go on there. I think it's interesting. I mean, there's been some interesting work over the years, but I'll just take the medical side for a second. In looking at Gricean maxims of communication, how do people report their symptoms when they might have a minor symptom that's giving them a lot of cognitive, that's at the focus of attention cognitively, that suppresses their discussing something more important clinically. Bayes nets have been built to counter this, or to automatically understand Gricean maxims of reporting of symptomatology, for example, and that correct for the sort of bounded resource cognition of humans that might focus on the splinter rather than the chest pain. This is work by Piot and Schachter a few years ago. You can look at that work.
One thing that's interesting about that, I'm actually just curious, it builds on the last question. How do you, in that work, think about people's own cognition of their own symptoms, not from this distraction point of view, but like, for example, I have, and I'm sure we've all had this experience, sometimes you just don't feel right. You know what I mean? Like, you're just like, I don't feel well. And people are like, well, what's the problem? I don't know. And I would never go to the doctor and say, I just don't feel well, get to work. So it's like, but yet we know that but you know, once you've named it, you've had a sense of it, and I know there's very specific examples. For example, lots of people come in and complain of heart pain or chest pain, when in fact, given where the nerves are located, that's very often stomach pain. But how do you know what I'm getting? Since symptom reporting is a big part of what you're doing, how do you even conceptualize the map between the physical body to the stated symptom?
So I was just talking to Jamie Pennebaker, who's a psychologist at UT Austin, who wrote a book called the Psychology of Symptoms and how they're reported. And he and I were having lunch. He was a visiting researcher with us over the summer. And we were just reflecting about, for him, given his career, what it would be like if he was told in 1965, when he wrote this book, or around that time, imagine a world where everybody is whispering their thoughts about their symptoms into microphones everywhere in the world, and it's being recorded somewhere, like in Google and Bing search logs. And then you could sort of go follow them for 18 months and then see what happened and understand how they spoke and what it might mean, including all sorts of terminology about malaise and not feeling just right, and so on. And was that the interesting signal that was linked to the pancreatic cancer that showed up later? And so all I'm saying is that we have those microphones now. They're anonymized, and we work with our ethics advisory board. It's scary to say microphones. That was just an analogy. I think we're going to learn a lot about how people talk, even when these things are vague. And our algorithms will be able to find sharp focal nodes, I think, from those what we consider vagaries of how we feel, if they're significant.
I mean, one interesting thing about that is how this stuff changes over time, in the sense that, once you've had a label put on something, then both you're going to express it differently, but also you'll recognize it differently. One of my earliest memories is being like 2 and getting ready for bed and telling my mother that I was sick and my head hurt and I felt funny and something was wrong, and she said, "Oh no, you're tired." I was like, "Oh, yeah, I'm tired." Now I know that feeling, right?
That was a good outcome, actually.
Exactly.
Oh my
But
God, a lot more things make sense to me now.
Yeah.
Holy cow.
If only your mother had been so
Yeah,
you were
Jesus.
too. But in studying sort of political bias
Yes.
speech, for example, something I've looked at in text, how loaded a term is in one year is very different than how loaded it is in another year, and just even how you use the Affordable Care Act versus Obamacare. Maybe it's when it's going badly and the website's going down and you say Obamacare, it's bad, but then when things are going well and everybody's getting covered, you say Obamacare and it's good. So those the time trends and that stuff is super interesting. Now you're looking at higher frequency data, so you can figure that out, but that itself is an interesting sort of study.
What's great about this is that there's this paper that is probably, I think, one of the 5 most cited psychology papers ever, but no psychologist, almost no one who's not a psychologist has ever read it, and it's just a beautiful paper. I would urge you all to read it. It's called Telling More Than We Know, and it's a whole set of experiments where they basically induce some behavior. They change the order of items, and they know that the reason you picked object A is because it came at the end or whatever. So we know the reason you chose object A. But then they ask people, why did you choose object A? And nothing in the language does anyone ever say, because it was at the end. So it's a beautiful paper that illustrates the disjunct between the true driver of choice and the language used to describe the choice. That's not to say that therefore language is useless. It's just to say there's this amazing divide between the language we use to describe things and what actually drives them, which I think that will be a very prescient paper over time.
Ravi?
So my question is for Eric. To what extent does our clinical drug trial process actually take into account what we know about after-the-fact interactions, right? So if I'm coming up with the drug today, I can prove that it does whatever I claim it to do, let's say by having a clean trial. But your work shows, and you can go out and look at logs and other stuff, that 2 years from now, this is going to interact with something else that's out there, and it's going to be pretty bad, right? So then what do you do about it, and how do we change the process about thinking about releasing new drugs, given what we know about that, right? I mean, just sort of and then who's at fault? Like, both these drugs are interacting and it's causing, something really screwed up. It's like, I don't know, I'm just want to see if there's any way to think about this even.
Well, certainly doing better and better and more open pharmacovigilance will lead regulatory agencies and pharma to think maybe more carefully about what they might say with confidence when a drug is released, and how they might invest in the pharmacovigilance process itself. Think about I think I heard that, I get to check my literature again, like the average person over age X is taking a mean of N drugs. And so the idea of these clusters, those common clusters of drugs that are being taken, certainly we want to look at the combinations and interactions. You think about interaction effects of 2 or 3 or 4 to the N, it's huge. And so maybe we have to wait for the real world to discover these things, but be ready and watching with our sensor array. One other comment is I told a large pharmacology company, I think with offices in this town, that we had this system, we called it Blair's. You can explore drugs and so on. And they got very interested in it, and I said, well, you want to see it? And they said, no, I really can't look at that right now. I just can't. And then I said, well, we're thinking of releasing it publicly. Oh, no, we want to see it first. Let us see it first. And so there's all these interesting legal constructs and that goes along with as policy folds in with regulation and surveillance. I think we're going to hopefully see rationality come to the fore, and more intensive processes, including near to the post-market release analyses that much more intentionally look at drug and drug interactions, weighted, for example, by distributions over other drugs out there and being taken at the same time.
So I actually had a question for Eric. Is policy, actually for the whole panel, but mainly for Eric, because I think you might have specific insight, is policy going to be able to keep up with all this specificity? So we're talking about very specific knowledge that we can now generate based on these new techniques. And I think we have an intuitive sense that policy is a blunt instrument. Maybe Amazon can personalize your recommendations, but can the government, for instance, really personalize things? And the reason I'm asking you is that personalized medicine may be a place where this can actually happen. So how well is policy going to be able to keep up?
So my sense is that there'll be a draw of people like those in this room to actually be in policymaking agencies. You will be relied upon for your insights and intuitions to help guide what's going on with where these inference methods and these data analytic approaches, hit where the rubber meets the road. Also, in guiding decision-making and in reflection, we have to, as a community, look out for very naive reactions that protect consumers in ways that will actually hurt them in the end. And we have to sort of be in that loop as well somehow by inserting ourselves into the conversation at multiple levels. Will it keep up? It'll keep up if we are part of the process.
Yeah, so maybe I'll say a few things about that. So the work I've been doing about heterogeneous treatment effects, ultimately, say a goal is that you could find a way to discover ex post a group that has very bad treatment effects or very good treatment effects that weren't in your pre-analysis plan, and have that be accepted by the FDA as evidence. Are my methods quite ready for prime time? Well, there's still ways that you can game them, like they're sampling things, and you can kind of keep resampling, and then you get a slightly different, so anytime there's any kind of randomization in the procedures with subsampling or whatever, you can get a slightly different result if you run the thing again, and so people could fish that way. So trying to figure out all the ways things can be gamed is a pretty tricky process, even though in some sense I feel like, yeah, I've got a better way to do it, but I would still have to think through in the bigger picture how you would implement that. Even for an A/B testing platform in a firm, you would have to think about, well, your researcher says, oh, well, just subsample again and you'll get a better, now we should ship my algorithm. So this is you got to be very, very careful with these types of things. And then I think there's a broader thing with personalization, like in lending, actually, there's all these restrictions about, non-discriminatory lending. And so if you're trying to now use very complicated algorithms, the regulations may not sort of keep up with the times, in the sense that, what really matters is sort of the disparate impact. And so, how do some of these things regulate like the variables that go into an algorithm, and maybe at some point the algorithms are just so complicated, you want to find some ways to sort of measure in the end, is my outcome fair, so that you can actually use things like, the zip code or things that are related that, you might in order to understand one variable, you might need to know something about the race of the person, but you want to find out in the end, is this a discriminatory algorithm? And so we don't really have a good science of that. I think some of the advances in, differential privacy and that whole space give us some promise for sort of a general conceptual framework to ask questions like, if I took this piece of data out about a person, would they get a fair outcome? Or if I change their race, would they get a fair outcome? Or is this model, there's some work that shows that, like, if you use a differentially private statistical algorithm, that you also are going to be immune to multiple testing. But I think we're really just scratching the surface of this whole theoretical area, and it's going to be a place with a lot of advances over the next 15 years.
But I'll also make a charge to ourselves, which is we have, on the policy front, I think we need to actually be at the forefront of not just guiding and helping, but also asking questions, even if they're controversial. For example, here's one at the top of mind. SSRIs, antidepressants, have been linked in young people to extreme, rare, but extreme violent behavior. We almost never hear about what drugs people were on when we hear these big incidents lately. It almost seems obvious at times these people were in the treatment and were on these drugs. And even though this is a recent, within 10 years, labeling change for young people taking antidepressants, we don't have good signals about this, and policy restricts us from gaining access. So we turn to our search logs, looking at folks that get interested in SSRIs, they seem like patients, and then look for shifts in violent interests and gun shops and gun pages, and you're looking for signal there, but we want to actually engage more deeply with the society as a whole to understand better occult or aspects of important data analytic problems that are hidden per privacy and current medical legal law.
The thing that I think is being alluded to here around how the skills of the people in this room can make quite a big difference. I'll just add an example that hasn't been out here, which is a lot of the things that people have gotten very good at, like recommender systems. Take that as an example. We know how to build good recommender systems. There is a shocking number of policy applications of recommender systems that can have unbelievable social value, but where those tools are not in government, where those websites are being built. Just to give an example, you're a kid who goes onto a website, fills out the Pell Grant application, which is a college loan application. With a little bit more information, you can then recommend that child where they ought to apply. Now, why is that so valuable? A lot of low-income children who are high achievers never realize that they would actually have a very good chance of getting into very good colleges. That is literally not money left on the table, but human capital left on the table by some of the most disadvantaged groups. Now, that's just a small example, but those type of examples permeate. So I think as people get comfort with these skills, but then start looking for other areas of application very quickly, I think we'll see, even in the government domain, even in many places, that these exact skills will translate into pretty high social impact.
So I was hoping you might comment on consumer financial protection, given your history.
I mean, I think that's exact. I thought your point about keeping up with the Joneses is exactly right. If there was an arms race between regulators and companies being regulated, it's like somebody showed up to a gunfight with a water pistol. I mean, regulators have nowhere near the skills needed to be able to ask questions such as, is this lending rule discriminatory? Or even questions such as, you have a complex algorithm that targets overdraft advertising. Deep in that algorithm surely is actually an algorithm that says, is this person going to abuse overdraft? Clearly it's an attempt to kind of get people to pay late, but somewhere regulators are just still very much stuck in this very old mode. And so I think it's almost like, if I were to use an analogy people here might get, it's a little bit like we have spam generators and spam detectors, but the spam detectors we have right now are sitting there, individuals looking at words, whereas the spam generators are using high-end machinery to generate spam. And that's kind of what we have in this important sectors like finance that goes with consumer protection. But even in asset markets, I don't think that, the guys regulating asset markets have teched up a little bit more, but I don't think they're anywhere near the level of a good hedge fund. So to the extent that there was lots of stuff going on, I mean, we have a big imbalance. And so you could argue we might be sitting on a time bomb. So.
Awesome. Maybe another comment was that you might get paid more at a hedge fund than at the FDA, so maybe we're getting a brain drain that way.
Awesome. Well, thank you guys very much. A really enlightening session. Let's thank you.